Hi everyone, Ms. Kilroy here. Today we're going to go over the notes for the states of matter unit. So now that you've glued in your notes, all you have to do is fill in the blanks. So make sure your notes are set up C-note style with a title at the top, summary at the bottom, and then on the left-hand side a notes and questions section. So states of matter, the definition is the physical forms in which a substance can exist. It's determined by how fast particles are moving within the material. Okay, so in material we have atoms and molecules that are constantly moving, and their speed determines what state of matter it's in. And there's 4 states of matter: solid, liquid, gas, and plasma. Now keep in mind, if I'm going too fast, you can always pause it or go back if you need to. Solids, they have definite shape and volume. The word definite means for sure. It has a certain shape. You can't really change that shape unless it breaks, and it has a certain volume. So particles within solids have little energy movement. They can wiggle in place, but they cannot move past each other. So they're just kind of vibrating in place here. So there's 2 kinds of solids. You have crystalline solids, where they're a nice, orderly, 3-dimensional shape. The orderly 3-dimensional arrangement of atoms or molecules, and some examples are diamonds, salt, and ice. And when you're drawing the crystalline solid, I want you to draw it in perfect rows. It's kind of hard to do in the computer. And perfect columns. So they all line up nice and neat, and they're all supposed to be circles. It's kind of hard to do. But that is a crystalline solid. An amorphous solid is where the atoms are in no specific order, and things like rubber, wax, glass, kind of things that are bendable. So think about like your eraser. If you can bend it, it's an amorphous solid. It's still a solid because it has a certain shape and volume, but it can bend. So amorphous solids are more kind of in any random order. So there's kind of spaces in between. It's not in those perfect rows. Okay, so this is an example, and then that is an example. So crystalline, nice and orderly, amorphous in a random order so it can bend. Then we have liquids. Liquids have no definite shape, but they have definite volume. So whatever container a liquid is in, that's the shape it'll take. So in this container, you can see that the liquid goes to the bottom, and they have little arrows because there's little movement. So these are supposed to be arrows. So they're sliding past each other. And these arrows represent energy. So if you could see in the solids, there are no arrows. They just kind of wiggle in place. I'm going to put a little vibration symbol. Okay, but liquids have a little bit more energy, and they slide past each other. So draw little arrows. Oops, that might even be too big. Little arrows sliding past each other. So they're still bound to each other, but they can still slide past one another, just like what I said. So liquids, there are certain characteristics of liquids. Surface tensions, the force of attraction, force attracting particles at the surface of the liquids. That's why you see those water striders, those water bugs that can float or walk on top of water in creeks. Viscosity is a liquid's resistance to flow. So a high viscosity means it has a hard time flowing. So honey, motor oil, really thick things has a high viscosity. And low viscosity means it runs quickly and smoothly, so water or rubbing alcohol. Gases. So gases have no shape or volume. So they just take the shape of whatever container they're in. They actually have no volume. Particles have more energy than solids or liquids, and they're not bounded to each other, and they can move about freely, and they collide often with each other. The more collisions there are, the higher the pressure. So it's kind of like if we decrease the size of this container, these molecules would run into each other more, and you'd have a higher pressure. So as you can see, the amount of energy is increasing. So starting with solids, they just vibrate in place. Liquids, they can slide past each other. And now gases have more energy. So draw the energy arrows longer than the solid, than the liquid ones. So like I was saying, pressure is the amount of force exerted in a given area. It's the number of collisions of gas molecules on the inside of a container. So here we have the same number of particles, but here we have a greater space. And if we decrease that space, there is more pressure. It's kind of like if you squeeze a certain portion of a balloon and the air molecules go to a smaller place and poof, balloon pops. Last example is plasma. Just like gas, it has no definite shape or volume, but particles have a lot of energy. Electrons are stripped free from gas. They're also called ionized gas. And atoms or molecules are surrounded by escaped electrons. And for plasma, you're going to draw it similarly to, similar to gases. So they take up the whole space of that container. Only thing that's different is plasma has the greatest energy arrow. So draw their energy arrows long. So these are some examples of plasma. The aurora borealis, like the northern lights, you can see it in Brother Bear. You can see the northern lights in Antarctica, Alaska area. And then they're in fluorescent bulbs, so the bulbs in our classroom, and then lightning. So they can conduct electric current, and they can be contained by magnetic fields. So here are the examples. And we'll get to this later, so good luck.